Hello everyone, my name is Jordan Glass, and this is Lab 5, Magnetic Braking with Faraday. So in this lab, we explored the interaction between an external source of magnetic field, a bar magnet in this case, and the magnetic field that is induced as a result of the external source. Specifically, we're to drop a bar magnet down a tube of aluminum foil and observe how its motion is different than if we just dropped it in plain air. Aluminum was used specifically as it is not ferromagnetic, so the magnet, when falling down the tube, will not stick to the side. We ran several time trials to see how long the magnet takes to fall completely through the tube, and then took the average of the different times. After this, we modeled the experiment in GlowScript to make a more precise simulation of what would happen when a magnet of a certain mass and dipole moment falls down a tube. So the models used in this lab were Faraday's law, magnetic flux. Like in Lab 3, we use the Biot-Savart law, the general form that works for all orientations. Ohm's law, Newton's third law, which you can see down here in the specific case of the experiment, and kinematic equations. So sources of error, one source is that when dropping it through the tube, we likely did not have it directly in the middle and it did not stay in the middle, like center line of the ring axis all the way through, which can affect the measurements. Also, a hand can apply some force or just it's difficult to uh, drop your hand specifically to make it not affect the motion of the hand before it falls. Some initial conditions: when the magnet was held above the tube, it had zero velocity and there was no induced current yet, there's been no change in flux. The system of the experiment consisted of the bar magnet, the tube of aluminum, and the earth. So in the experiment, the tube we used was 30 centimeters, width was 0.01 meters, inner radius was 0.015 meters, magnet was 0.026 kilograms, dipole moment was 4.22 amps times meter squared, which was the same value we used in Lab 3. Then these were the time trials with an average time of 2.416 seconds. So first, we're given some essential constants and input the specific data for our tube in the experiment. Then we filled in the mass of our bar magnet as well as dipole moment we calculated for back in Lab 3. We also used the same magnetic field of a dipole function that we created down here at the bottom. That was also made in Lab 3. Then we made a function that could calculate the magnitude of the change in flux over time, which is also equal to the EMF induced in the tube. Finally, we used previous functions to make a loop that would iterate over the ring in the tube and calculate its force on the magnet and add it to the total force on the magnet. We used this data along with Newton's third law and some kinematic equations to keep track of the velocity and also the position of the bar magnet. So when running the simulation, my code unfortunately did not work entirely properly. Some error occurred and the graph did not look like it was supposed to. But on the right is how the graph is actually supposed to look, thanks to someone on Ed Discussion posting it and asking for clarification. But yeah, this is how it should really look if your code was working properly. So yeah, interpreting the simulation. In the ideal graph simulation, there's a long period where the velocity does not change, indicating the forces during that period are equal and opposite, making it no acceleration. What if the resistivity of the conductor were reduced as close as possible to zero? This would result in a much greater current and thus a higher magnitude of force on the bar magnet. The magnet would thus fall much slower. What if holes or slots were cut into the tube? The tube could no longer be cleanly iterated over the length of the tube in the model, as different rings would have different circumferences and would maybe not even be able to be modeled as rings depending on the severity of the cut. In conclusion, we observed that a falling magnet will induce a magnetic field in a tube of aluminum, which results in a magnetic field and upward force. This increases the amount of time it takes for the magnet to fall when compared to just falling through air. And this can be modeled in GlowScript by treating the tube as many rings of wire and iterating over the length of the tube. Thank you for watching.